start out with the challenge problem from the last video. So of these three scenarios, where would the string be most likely to break? And I gave you the hint to draw the free body diagrams for each of these boxes, and that should give you a major hint right there. The answer is box C, and let's go over it really quick with the free body diagram for box C. So we have force of tension 1, force of tension 2, and the force of the earth. Alright, so for each of these boxes, the vertical components of tension have to balance the weight of the box. Alright, but box C has the majority of its tension horizontally, right? Because you can see that from the horizontal, smaller theta means a larger horizontal value. Therefore, to have the vertical components of tension balance the force of the earth, we have to have a larger value of tension as a whole. So that means that the tension for box C will be greater in order to balance vertically the weight of the box, and a larger tension value means the strings are more likely to break. In this video, we're going to be looking at Newton's three laws. So Newton's first law states that, you may have heard this phrase before, an object in motion will remain in motion unless acted upon by a net external force. Right? So to look at this, we need to be familiar with the concept of a system, which is really just a group of objects that you are considering sort of to be like one object. So, for example, let's take a look at, let's say we have a wagon, and let's say we just have a collection of objects in that wagon, and we have two people who are going to be pushing on it. Sort of like that. They're both pushing on this wagon. Alright, let's consider the system to be the wagon. So I'm going to put like a dotted line around it. That is our system. Alright, the force of these two people would be an external force. And it really doesn't even matter that there are two people. No, we could replace both of these people with one larger person who's going to be exerting the same force on the wagon. Alright, and this will get really crucial when we get into energy, but just think of a system as a group of objects, and Newton's first law says that an object in motion will remain in motion unless acted on by a net external force. So if we were to consider this person to be within our system too, then this system would have no external forces on it. Alright, so let's look at another, maybe a quick example / problem to illustrate this. So let's say I have a block that is sliding along a frictionless surface, so there is no friction here. Alright, Newton's first law would say that this box will continue on with the same velocity, meaning it's not going to change directions, same velocity, same direction, indefinitely, until there's an external force acting on it. So maybe that force acts to speed it up, to increase its velocity. Maybe it acts in the opposite direction to the left here, to slow it down or change its direction. But until that external force is applied, this block is just going to move to the right forever with some velocity v. Alright, Newton's second law we covered in the last video, but there is one more thing I want to point out. So remember, this is the equation F net equals ma. So remember, when you're solving for the acceleration, or maybe in some cases for mass, that you need to use the net force on the object. So you can't just pick and choose what forces you want to include. And these are typically, all the time, external forces. So make sure that you know what system you're analyzing when you are picking out and summing the forces. But really quick, let's say we have a box. We have a force magnitude F here, and a force of magnitude F here, right? So we know acceleration then equals our net force divided by mass, right? We have two forces of the same magnitude in the opposite direction, so that's just going to give us an acceleration of 0 meters per second squared, and that box does have a mass m. But just because you have two forces that are essentially canceling, so there's really no net force. The net force on this box is 0. But even though there are two forces acting, this box could still be moving. It could be moving with a constant velocity in either one of these directions. But unless you're told otherwise, it could be moving to the left, right, or it could not be moving at all. We just know that it has an acceleration of 0 meters per second squared. So don't be fooled by seeing these two forces in the opposite direction and thinking that the box is not moving. Additionally, a lot of times, like in this problem, the system will be sort of implicitly mentioned. Like here we're just saying the box, clearly we're defining the box to be the system. Alright, so Newton's third law can be a little bit misleading. So if object A exerts a force on object B, then object B exerts a force of equal magnitude on object A. The misleading part is that quite a few times you might hear it referred to as action-reaction forces, and I'm going to show you why that can be quite misleading and why you want to think about it in terms of object A and object B. So let's say we have a table, and let's say we have our favorite box on that table right there. Let's consider the force of the earth on the box. Right? If you're following the analogy of action-reaction forces, then you might think the reaction force is the force of the earth on the box. Since the earth is pulling the box down onto the table, that maybe the reaction force is table on box. But that's when you need to think in terms of object A and object B. So actually, let's consider A to be the box, and let's say B equals earth. Right? So if A is exerting a force on B, that would be the box exerting a force on the earth. And in response to that, the earth is exerting a force on the box. Or you can think about it the other way around. You could think the earth is exerting a force on the box, so the box is exerting a force on the earth. So the reaction force is actually the force of the box on earth. And there is a really quick and easy way to figure this out. So I'm going to get rid of this. And we are going to we know we have you're given the force of the earth on the box as F sub EB. Then you can think of the reaction force, you just switch the subscripts. So now we have F sub BE. Right? Of course, this raises the question of the box is exerting force on the earth. So, but they're not in contact, and that's okay. Gravity is a non-contact force. But if we were to put this box in free fall, if we were to take away the table, then doesn't the earth move? The answer is yeah, but look at Newton's second law, A equals F net over m, the mass of the Earth is extremely large, that it has a minuscule acceleration that is pretty much negligible. Anyway, let's look at some more practices with these subscripts. So let's say we have the force of the table on the box. What is the reaction force to that? Think about it. Switch the subscripts. The reaction force to the force of the table on the box is the force of the box on the table. So the box really pulls up on the table, kind of like it pulls up on the Earth as well. But again, we don't really notice the Earth part of it because the Earth has such a massive mass. And one more, let's say we've got the force of the Earth on the table. What is the reaction force? That would be the force of the table on the Earth. Alright, here's a quick practice problem to really pull everything together that we've learned. So the truck exerts a force of 100 newtons on the trailer. What is the force the trailer exerts on the truck? So we're going to be referring to the truck as C and the trailer as T. So we are given F sub C of T, and we want to find F sub T of C. So notice that the variables in the subscripts are reversed. So that means we've got a Newton's third law force pair, or you could say carefully an action-reaction pair. So if F sub C of T is 100, then F sub T of C is also 100 newtons. They both exert forces of 100 newtons on each other then. Part B, the truck lets off on the gas and the ground exerts a force of 36,000 newtons on the truck trailer system. So that really just means we've got a force of 36,000 newtons acting to slow the system down. What is the acceleration of the system? So using Newton's second law, we can say that acceleration equals F net external, because the ground is external to the system and it's exerting a force on the system, divided by the mass. So think, should 36,000 be a positive or a negative value? Hopefully you said negative, because it is acting opposite the direction of motion and it's slowing the system down, divided by the mass of the system, which is the combined mass, right? So really here it doesn't matter if we've got a dozen objects so long as they have a combined mass of 6,000 kilograms, where we can really just think of our system as one large object that has the same properties of all the objects within it combined. So then we have a mass of 6,000 kilograms. And you can drop the zeros, and we are left with an acceleration of negative 6 meters per second squared. Alright, here's the challenge problem for this video. You can read it, and the answer will be on my Instagram page about 24 hours after the release of this video. Link in the description, or you can find it at the beginning of the next video. And a really big hint for this problem is to first use Newton's second law, and second, draw free body diagrams. So good luck.